Hello, welcome to Electronics Education. This is Vincent Chang. In this lecture video, I'm going to teach you operational amplifier as a differential amplifier. Op-amp as differential amplifier. This is the circuit we want to study in this lecture. On the right-hand side is differential amplifier, which is composed of one operational amplifier and four resistors, R1, R2, R3, and R4. Two input and one output. Two input on the left, V1 and V2, one output. So because it's the linear network, so the output voltage can be expressed as the linear combination of the two signal, right? So this is the form of the linear combination. VO equals A1 times V1 plus A2 times V2. So if you have an equation, a relationship around the linear combination form, then how are we going to solve this? How are we going to solve this? And the next question is, what about can you just use the analysis by inspection to decide the polarity of these two coefficient? The first one, the A1, because the A1 is the coefficient of the V1, right? And the V1 comes in through the negative input, the inverting input. So A1 should be less than 0. And A2 is the coefficient of the V2 and coming in through the non-inverting, the positive terminal. So A2 should be positive. So if you given the random number for the four resistors, it could be negative 1 V1 plus 3 V2 or negative 5 V1 plus 4 V2. So it's the conditional differential amplifier. So this is not necessarily a differential amplifier. It's the conditional. What condition? If it's negative 1 for A1 and 1 for A2, and then it's differential amplifier. If negative 2 for A1 and 2 for A2, it's going to be a differential amplifier. If the two coefficient, the magnitude of the two coefficient can be adjusted to be the same, then you can pull out the coefficient, then the VO will be proportional to the difference of the two signal. All right? So the concept I want to notice is this. The differential amplifier is conditional. It has to meet a certain condition associated with A1 equals negative A2. The next question is, how are we going to solve this if the relationship is built around the linear combination, principle of superposition? You can just set V2 as 0. Just kill the second signal and focus on the contribution from the first signal, V1. And then you can set the V1 as 0 and focus on the contribution from the second source, A2, V2. And then you combine these two together, you will get the result, the linear combination result. Let's dive in to analyze this circuit. Let's say if V2 is 0, focus on the first contribution from V1. Then what's the answer? This is easy, right? This is easy. The answer, inverting amplifier. Negative R2 over R1. What about the next one? The right-hand side. Let's set V1 as 0 and focus on the second contribution from the second source. What's the answer? This should be easy as well, right? The same current. So divider. So the V negative, the inverting voltage, the voltage at the inverting terminal should be VO2, and then what? Times the ratio. What ratio? R1 divided by R1 plus R2, voltage divider. The voltage divider. Okay, let me take out my video. All right, because they share the same current. Same thing with the V positive. Same thing with the V positive. And virtual short. Negative feedback. Ideal op-amp. You can equate these two voltage together. Virtual short, you will get this result. All right? Therefore, based on the principle of superposition, you simply add these two terms together. The contribution from the V1 and contribution from the V2, then here's the outcome. It tells you the A1 is negative and A2 is positive, right? And then what's the condition to institute a differential amplifier? The same magnitude from two different coefficients. Naturally, it's opposite polarity. But you need to adjust to make the magnitude of the two coefficients becomes the same. Then it becomes the differential amplifier, right? So if the R2 over R1, then V2 minus V1. If it's the differential gain is negative R2 over R1, then V1 minus V2. So what's the condition? The two coefficients, the magnitude of the two coefficients should be the same. If you do a little bit math, it will give you this outcome. It will give you this outcome. Ratio. If R1 over R2 equals R3 over R4, which is equivalent to the A1 equals negative A2. I don't want to go through the math detail, okay? It's your job. Okay, this is middle school math. Okay, I'm not going to teach you this. It's your job. So if the relationship holds, the ratio relationship holds, R1 over R2 equals R3 over R4, then it becomes, this is true, it becomes the differential amplifier. So that's the condition. That's the condition. The original circuit is not a differential amplifier, but through this relation, if this is true, if you then meet this criteria, then this circuit is differential amplifier. And the gain is R2 over R1, differential gain. Let's see another characteristic. So see this slide. Now it's the ratio, right? R3 equals R1. R4 equals R2. So R2 over R1 equals R4 over R3. So it's the differential amplifier. So let me ask you this. What about the input differential resistance? In other words, the resistance seen by the differential source input signal. The resistance, the input resistance between the two blue nodes. The input resistance between the two blue input nodes seen by the input differential source. Intuitive analysis by inspection. Two, right? So two blue nodes. So R1 in series with a short circuit called virtual short, and then in series with a second resistor R1. So it's 2R1. But how many students? Some students is gonna wonder, this could be true or false? What about the op-amp? What about R2? So for a beginner, if you have this kind of doubt, then you have to prove. You have to derive based on the KVL, kickoff voltage law. Then you can write down this, right? The source. The first drop, IR1. The second drop, virtual short. The third drop, IR1. And then the definition of the input differential resistance is defined as the differential voltage divided by the input current. So it's actually 2R1, no problem. Here's the takeaway. Remember, it's the conditional. Has to meet a condition. If the R1 over R2 equals R3, only this criteria, when the circuit meets this criteria, can this circuit become a differential amplifier. So it's the conditional differential amplifier. The second, there's a trade-off between the gain and the input resistance. Because on the left-hand side it tells you the gain, the differential gain. And also, we analyze the input resistance is 2R1. So if you want to have the high input resistance, R1 should be as high as possible, right? But it will downgrade the gain. So high resistance, high input resistance, the high differential gain, you can have both. You have to trade off. That's the downside of this circuit. You have to sacrifice one way or the other. That's the downside of this circuit. So how to improve? How to overcome this downside? Further improve to have both. Then that's the answer you will see, the lesson you will learn from the next lecture called Instrumentation Amplifier. Looking forward to see you in the next lecture video around the instrumentation amplifier. Thanks for watching.